Well, welcome to session 1C. It looks like we're off to a roaring start with Living to 100. And I just wanted to just very briefly introduce Stefan and myself, who are speaking to you today about measuring uncertainty. We realized just a moment ago that we have to say that we're measuring the uncertainty of the baseline. Steve Holbert pointed out that we actuaries are more worried about the baseline than relativities, but we'll also see that those relativities have quite an important impact on our models as well. So very briefly, welcome to our session. My name is Kai, and I'm from NMG Consulting. I have worked as a reinsurer and as a consultant for the last 20-odd years. And in my work, I have to not just make predictions, make pricing predictions or measure reserves, but I also have to be able to say how good those predictions are. That's something that we all learned at school, that we shouldn't write down a number without being able to write down what the error is that's associated with that number. But it's something that in practice we often forget. So in today's session, Stefan and I want to show you easy techniques how to actually do that in a quantitative way. Stefan, I'll let you introduce yourself, and just so that you get used to it, we're going to be tag teaming it throughout. One of the reasons we do that is we want to encourage you to interrupt us and ask questions as well. If you do so, since the session is being recorded, please, if you could step up to the microphone, very briefly say hello and give us your question, that would be great. Thank you.
Yeah, so I'm Stefan Ramonat, and I work for Mercer in Ottawa. And over the last 4 to 5 years, I've been involved in developing our internal mortality modeling, and so I've done analysis for lots of large plans, large pension plans in Canada, and also developed what we call the Mercer mortality model, which we'll be using for a lot of the examples that we'll look at today.
So. Who are you? Just a quick show of hands for the demographer and us. So exactly, who are the demographers? Okay, we have a token demographer from the medical profession. We have, 3. Who's an actuary? Okay, that is overwhelming. Within the actuarial field, how many people are more on the pricing side, would you say? Okay, and more on the valuation side of things. Okay, great. Glad to have you here. Let's get going. I think I left the tag thing. So okay. So it looks like we're out of a slide right now. Okay. So we in our session, we just want to very briefly give you an introductory warm-up example. Then, having motivated why we think it's actually really useful to think about uncertainty, take you through some of the technical background, including a snippet of our code to see just how easy it is to do this. And then Stefan is going to show you his mortality model for Canadian pensioner mortality as a case study, and I'll at the end throw in a couple of other applications that might be interesting to you as well. So without further ado, let's figure out why it's actually worthwhile worrying about uncertainty. So we can't do a poll, but because we can't do a poll, it's probably better if we say what, from our perspective. Okay, so maybe you just want to do it on the laptop, because I think it might be the signal. There are a number of reasons why measuring the uncertainty is important. In the first place, you're trying to come up with an estimate. You're trying to come up with an idea or a basis that you want to use either in pricing or in valuation. And you need to know how good that is. You need to know whether the answers that you're getting make sense and whether the differences in answer are actually large enough that you can measure them. That's why, from a research perspective, measuring uncertainty is very important. But if you're in the insurance industry or in the pensions industry, the regulator will have a word to say about that as well, because uncertainty also it has an application with measuring the margins that you have to hold against future liabilities. Capital assumptions, internal capital models effectively also use the uncertainty associated with the risk, and there are a measure for that uncertainty that you need to allow for when you're actually capitalizing your company. And finally, if you actually are taking on the risk, or if you're advising on taking on the risk, you really need to be able to measure the risk. And risk itself is just the uncertainty of an event. Not that the event will happen, but when it will happen and what the outcome will be. Okay. So I'll hand it over to the Canadian actuary to talk you through Canadian pensioner mortality.
So just for sort of a warm-up example, we thought we would use a standard mortality basis that's well used in Canada and where the data is publicly available. So this is the CPM 2014 pensioner mortality table. So the classic approach to assessing the mortality, the estimation error for this group would be to calculate the Poisson standard deviation, so just 1 over the square root of the deaths. So in this case, we would have a standard deviation around the mortality rates of about 0.4%. And then we would assume a normal distribution to develop confidence intervals. And so in this case, 95% confidence interval would be about 0.8%. So this is 0.8% around the mortality rates themselves. But the thing is, we don't really necessarily care about the uncertainty around the rates themselves. That's just an intermediary step. What we really worry about is the error around, say, the liabilities, the reserves, or some other measure. So we can take the uncertainty around the rates and translate that into the uncertainty around liabilities, say. And in this case, the 95% confidence interval would be about plus or minus 0.24 around the median. So for the rest of this presentation, we'll mostly be talking about uncertainty in terms of liabilities or reserves, not in terms of the rates, but they're sort of interchangeable.
Yeah, I think the main thing that Stefan and I debated a lot was why do we even worry about the uncertainty in the rates? That's because the mortality table is the tool that we use to calculate the life expectancy or the reserves, but it's not the actual outcome of our calculation. And as a freshman, I learned error propagation. So if you actually have uncertainty around a certain ingredient to your calculation, that will actually balloon as you go through a complicated calculation. So why not try and measure the uncertainty of the final outcome instead of the uncertainty of the intermediate step?
And the other thing we were debating is, so I mean, Kai and I, in our own work a lot with parametric models, fully parametric models, but in different applications, it may make more sense to use sort of semi-parametric or even non-parametric methods such as penalized splines. And you could even just use the crude rates as they are, depending on if you have a large data set and depending on what purpose it is. So we thought, for this example, we would show what the misestimation ranges are under various methods. And so we just picked 4 here. We're not going to get into the details of these models in this presentation, but we should note that one of the ones that we use the most is the Macon-Perks model at the bottom there, and we'll see later that it has a lot of properties that are very nice for pensioner and annuitant mortality. So here we show we compare the misestimation confidence intervals, and at this point we haven't shown you how we calculate these. That's going to come a bit later. But the first line there is just the classic approach, the one with the Poisson standard deviations that I was just showing. And the other ones are under the misestimation framework that we're going to explain later. And we see that in this restricted case where we're dealing with a very big data set and we're only calculating the liabilities up to 95, age 95, the misestimation ranges are actually identical depending on which method we use to model the underlying rates. But what I should point out, though, is that the classic approach here, I mean, that was just calculating the standard deviation, and we can almost calculate it on our calculators, while the misestimation, while not horrendously complicated, does involve more mathematics, involves having more results available to us, and it also involves having thousands and thousands of simulations. So there's a lot more work involved, even though we get the same answer.
So you're probably sitting here thinking, well, why are we here in the first place if it's so easy and it doesn't really make a difference? What's the point? Well, the point is that you shouldn't just be worried about the uncertainty in the mortality rates at an aggregate level. We're really interested in understanding the mortality, for instance, of different risk groups within that larger group, or we're interested in refining the model even further. And being able to measure the uncertainty, the estimation error for that model is going to help us decide which model to use. That's one of the main applications that we want to talk about today. And it'll also show us how the impact of one individual risk group can actually have can be very important and have a big impact on the overall liabilities. So the question is, do I actually have enough statistical credibility to use that information about that group? And what's the trade-off? Okay, so it looks like here we go. So stepping into just after, hopefully, you're warmed up to the idea that we want to spend a little bit of time on some technical work. Just want to classify what the different components of risk actually are. Focusing on the top two. First of all, you have stochastic risks. So whether Ronnie dies or not is really a random thing, except if he gets me really annoyed. But even if I were to know the exact probability of a certain event happening, it's still a probabilistic event. So I guess we all agree that. So you can model that probability, you can model the uncertainty that arises from mortality or morbidity being probabilistic. The second part is we've estimated those probabilities based on a finite amount of data. There is no infinite data set that can tell us exactly what the model should be, what those rates are. Those are always estimated on a finite data set, and that data set will govern how good the model is. The other three categories are ones that we, as actuaries, often worry about as well, but in reality, they could be seen as subsets of the top two. So if you think about trend risk, for example, if you parameterize the trend, if you measure the trend in terms of your model, then measuring the trend and the uncertainty associated with that will be a combination of process risk and estimation error. Same with catastrophic risk or basis risk. Basis risk is a risk that we'll speak about a lot more towards in the second half of the presentation, where we're essentially trying to balance how good the model is with the uncertainty associated with that model. So this is with respect to process risk. It's actually very, very simple to simulate. Again, there's a classic approach of taking a portfolio and letting it randomly die at every interval, at every time interval that you're interested in. But a much more efficient and more performant method of doing that is to just take the inverse of that survival curve that we know. If we know the mortality table, we also know the survival curve, and randomly pick a probability between 0 and 1, and that'll tell us, let's say if I throw the dice and I find 0.3, that'll tell me that for this particular life, I've got a 29-year remaining life expectancy. So I can very quickly generate essentially a random data set of future lifetimes that I can analyze with respect to the liabilities or any financial outcome that I'm interested in. So we've written down the pseudocode. So essentially, you go through your entire portfolio, you simulate the lifetime for each individual life, and then you do the whole thing multiple times. And that's essentially your Monte Carlo simulation for the runoff of that portfolio, given whichever model you have. Now, and just to be clear, a simple non-parametric mortality table is also a model. That'll give me a survival curve that I can use in this way. So it doesn't need to be a beautiful little continuous time parametric model like we prefer. Okay?
So just a quick example of that. Here we have a group of 500 individuals, and we ran 100,000 of these run-off simulations, which is way too many. It's just to drive the point home. And since we were using a fully parametric model, where we could get a nice equation for the survival curve, it was very, very quick. So even on my rather unimpressive laptop, it took under 2 minutes to run all 100,000 in this case. And the result we get, the main result that we were interested in here is what the histogram is illustrating. So the distribution of liabilities that are realized under these simulations. And in this case, for example, we find that a 95% confidence interval, just because of runoff, is about plus or minus 4% in terms of liabilities. So to be confident that you can, the margin you would want to have a 95% confidence that you'll be able to pay all the liabilities just because of runoff would be an additional 4% of liabilities in this case. So we're skipping ahead again to show to try to show the combined effect of misestimation and runoff just before we officially get into misestimation. So here we have three sample groups. They were all sort of subsets of a single larger group, where we have in the first case 500 individuals, about the second one 1,500, and then 15,000. And what we did was run, again, 100,000 simulations of just the runoff, just the misestimation, and then the misestimation and runoff together. What we find, which shouldn't be too surprising, is that as we get to bigger and bigger groups, both the runoff and the misestimation ranges become much, much smaller. And what we also see is that there is a diversification effect between the two risks, so that the sum of the two is nowhere close to the effect we see when we do them at the same time.
So when you look at this, essentially this delta peak, if you've got a large enough group, you don't really need to do any statistics anymore, do you? Well, that's the fallacy. Of course, if all I'm interested in is the average mortality of the entire group, then I get this sharp peak. But if I actually add additional risk factors, as we'll see in a minute, that peak will widen, or the distribution will widen, and it actually becomes more of an issue. But this is also, from my perspective, the excuse that we actuaries have been using why we haven't worried about uncertainty, because it's such a nice tight distribution here. Okay. Yes, the pedestrian way. So how do we do misestimation? So the most straightforward way is to essentially re-simulate your data. So you've got, let's say, an aggregate data set, like you've got human mortality database information, you've got deaths and exposures, and you just need to assume the underlying distribution that generated those deaths, and then you can randomly simulate deaths at each cell, pretty much, at each age and year where you have information. or if you have multiple risk classes, for each risk class, for each age and year. You just resimulate the data. So you've got a new data set, you fit it, and then you calculate your liabilities based on the newly fitted model. That is a little bit strenuous, and it breaks the laptop for sure. So the alternative is to use a little bit of math. Okay? So since so many of us raised our hands when Steve asked us whether we recognized the Cox simulation, so you may not be too scared of having a survivorship multiplied by a force of mortality being the probability of dying at any given point in time for each individual. And that's really all the likelihood is. And if you maximize that, you can essentially fit a parametric, semi-parametric, or non-parametric model. But the beauty of having a parametric model is that you can then use the properties of your maximum likelihood estimation, which was the next slide, I think. So it's a little bit busy, my apologies, but the key message is if you've got a maximum likelihood estimation of your model, you can use the properties that close to the maximum, all the parameters behave like a normal distribution. So if you give the model a shake, it'll react as if each of the parameter estimates are normally distributed. And that actually makes for a much faster simulation.
Yeah, and because when we're fitting under maximum likelihood estimation, generally for free, or at least with very little work, we get the variance covariance matrix that defines the multivariate normal distribution, which we'll show some examples of in a second. So we'll follow, just for an example to show some numbers, we'll in the first example with the Canadian pensioner table, one of the models we used was the Macon-Brooks model, which I said we'll be coming back to quite a bit. So the table there has the maximum likelihood estimates for the three parameters for the Macon-Brooks model. The alpha and beta are the intercept and slope, basically of a line in defining mortality in a logistics space, and then the epsilon is the Macon term, so it's finding excess mortality at younger ages. The plots we have there are the profile log likelihood plots, which are the likelihoods in the vicinity of the maximum likelihood. In this case, by each parameter. In this case, within a 95% confidence interval of each parameter. And the fact that it's so quadratic, for the most part, is a function of the normal distribution. And so we see that outside of the peak, they start dropping off very quickly, and so that makes for a good estimate and makes for a meaningful covariance matrix.
Just a nice little fun fact. This always reminds me of why the Fisher information actually works the way it does. The greater the curvature, so the tighter the peak is, the more information you actually have along that particular dimension. So I think it's always a useful thing to remember. And if you've got a very flat estimate, or you've got a very flat partial log likelihood, that means that your parameter isn't actually that useful. Yeah. Here we go.
So here we have the corresponding variance covariance matrix. This is the black table. So along the diagonal we have the variances, and then the other. And then the off diagonals are the covariances. The red table there, that's a corresponding correlation matrix. So we see that these parameters are very closely related, which makes sense. I mean, if the alpha and beta are the slope and intercept of a line, basically, then if you change the intercept, well, the slope has to change sort of in the opposite direction.
So just before we move on, this beta, that's essentially that's the thing that measures aging, and that's where, unfortunately, we didn't quite get that question in with Steve in the earlier session. But this correlation here says that if you have lower mortality, so if your alpha is lower, then your beta is going to be steeper. So if, for example, if females have lower mortality than males, they will also have a steeper slope. So they'll age more quickly, and that's the opposite of what Steve said before. So I still need to capture. But it gives you a bit of an intuition around what those parameters mean.
So with this table and with the maximum likelihood estimates from the prior slide, we have the mean and the covariance matrix for the multivariant normal distribution. To be able to actually simulate things, though, we need to basically find the multivariant equivalent of the standard deviation of just taking the square root of the variance, like we would in a single parameter case. And for that, we use the Cholesky decomposition.
So before you get scared, you get this for free in R, so you don't have to actually figure out the math. Sorry.
Yeah, and so this is the last. So the numbers not necessarily making sense by themselves, but this is the last step we need to be able to actually run the misestimates and simulations.
Okay, so again, I tried to write down like the pseudocode. What you do is you've got your maximum likelihood estimates. So you've got a vector of parameters, and then you try to disturb them or perturb them. But you have to do that in a way that's consistent with the data. And your variance-covariance matrix or its Cholesky decomposition actually allows you to do that with a set of random numbers. But yeah, Stefan told me that this pseudocode isn't actually as nice as the R code itself that you use to run this. So let's flip.
So I think I want to have to end the presentation and then come back into it, unfortunately, but
yeah.
It should work.
There we go. Maybe just a sec. Yeah.
Yeah. So I've loaded the data that we used for the warm-up exercise, and I just loaded the maximum likelihood estimates and the variance covariance matrix. The reason I'm not going to run it here is that it takes a little bit of setup to run the Macon-Perks model, but it's very easy to run a simple model. So here we're just going to run what's effectively Gompertz. It's just a GLM with an intercept and a slope. There's no other parameters. So, oops. So R gives us the intercept and the slope. And you see we have the standard errors here automatically from the GLM. But we also get is the variance covariance matrix. So just with the variance covariance VCOV command, for most well set up R models, we get the covariance matrix for free. And might as well show the correlation as well. So you see we have between the intercept and the slope, it's almost completely negatively correlated, which makes sense again because in this case it's just a line. So I have the variance covariance matrix from the slides loaded here, and then get the Cholesky decomposition. And just to show how these things relate, if I multiply the Cholesky decomposition by itself, like the cross product, then we just get the variance covariance matrix back. So it's basically the square root.
Jean-Marc.
Is it base R?
Yes.
Everything here is basically base R. So now to simulate it, then, so here are the maximum likelihood estimates. But simulate is just taking, in this case, 3 random normal 0, 1 variables, multiplying it by the Cholesky decomposition, and then adding that to the mean, to the maximum likelihood estimates. So there's one simulation. So you see then the results are close to the centrals but different. Can run it again. We'll get slightly different numbers but still consistent. And just to see that a little easier, this is running it directly. So here we've taken the Cholesky decomposition because it's easier to then run it in a loop. But if you just want to have a set of random variables, we can just calculate we can just run the simulations directly using here the MVR norm function. And so here I'm getting 10 different parameter sets that are all consistent with the data and the model, but are different and will result in different liabilities.
Okay.
Any questions on that before I switch back?
Yeah, Roland, what's...
You said initially that you're using the optim function?
So,
or was it just some introduction, but you used the GLM then, right?
So we use a GLM there for the example, but in practice, if I'm fitting something in R, I end up using optim just because I need more flexibility. So if you're using optim, it can return the Hessian, which you need to get the covariance matrix, or you can calculate it outside of it as well.
Okay. Oh, there we are. Okay, back to the presentation. So just as a reminder, you can do misestimation whether you have a parametric model or a non-parametric or semi-parametric model. We happen to prefer parametric models because the parameters actually give you a couple of nice additional features. If you have a model where the parameters have a useful intuition, like the alpha being the intercept or the beta being the slope, essentially the rate at which people are aging, then you can actually interpret these parameters if you apply them to different risk groups. So then you can essentially you can compare the risk groups using those parameters, and that gives you a very nice intuition for what the model is doing. But at the same time, you can also understand what adding that additional level of detail does to the overall model, to the quality of the model and the quality of the fit. In other words, the estimation error. Parametric models also have some additional cool features. They easily extend to old ages, which is something that I like particularly because it's applicable for 100 or 110-year-olds, your supercentenarians, where we still have too little data today. Parameterizing a trend is also a really nice way of measuring uncertainty that is important for a practical decision that you have to make. How much data will I use? Will I only use the most recent data, or will I use essentially decades worth of data even though it may not be relevant? And misestimation helps you essentially just come up with a quantitative way to make that decision. Very briefly, because we don't have a huge amount of time, this is just listing the different parametric models that we like and we use that have been around literally for hundreds of years, going back to 1825 when Gompertz wrote down his function expressive of the nature of mortality, up until the 50s of the last century when Beard published his model. And just as a little living to 100 snippet, this row here is our living to 100 parameter. It essentially describes the asymptotic behavior of mortality at old ages. Okay? So if you can actually fit that in your data, that gives you the level of the mortality plateau. Okay? I've written down the formula here because when I first was introduced to these models, I said, well, what's the point? Or why do you want me to do math again? But when you see that each risk factor that you want to add can actually be implemented really easily by adjusting the parameter. So if I want to include a main effect, for example, for gender, I can have a baseline for males and an additional adjustment if the individual happens to be a female, or smokers and non-smokers, or different pension amounts, or any kind of risk factor that might have an impact. So I can not just include it in the model, I can also measure whether it has a significant impact and whether it actually belongs in the model or not. Okay, so that's it. Yeah, so here you go. Fair enough.
Okay. So we just had a very quick example here where we're building up a model using sort of classic, well-known risk factors, such as gender, first versus second life, blue versus white collar, and pension amount. So each one of these factors changes the liabilities, hopefully gets closer to the true mortality level. But what we also can measure, though, is the impact on the misestimation ranges. So here, by building up this model, we basically end up just over doubling the misestimation range from the base model compared to the more built-up one.
So going from 0.47, so a very narrow confidence interval, to 1% confidence interval. This is a pretty large data set, so we have tight bands. But when you go down to hundreds of lives, then all of a sudden these ranges become bigger and you hit the boundaries of what's still useful. That's the extrapolation that I just mentioned, just to prove the point that you can get to really old ages even if you run out of data, as long as your parametric model makes sense.
In this example here, we thought is a good way to sort of show some of the applications of misestimation. So this is a big data set, 150,000 deaths or so over 11 years, so from 2007 to 2017. With the parametric models, we can incorporate the trend in some fashion. So with make and perks, this is how we can do it. We just add an additional parameter. Though in this case, it's very powerful but not flexible. So we need another kind of model, which we won't get into here because it would take the whole presentation. But it's more flexible in how we can handle the trend, and so we can have either a constant trend over the whole period. It still varies by age and everything, but it's the same trend in 2007 that it is in 2016. Or we can model a single trend change from the data if it's supported. In this case, so the blue dots are is the trend expressed as the trend is the mortality expressed as ratios of the mortality over the whole period. So we see that there's a very strong downward trend up until 2013, 2014, and then it starts getting more volatile. Like it's been seen in many countries over that period. So using the parametric models, using maximum likelihood estimation, we can find that the best fitting model is one where there's a single trend change around the middle of 2013. And so that's the green line versus the red line, which is just a constant trend. So not surprisingly, we end up decreasing the liabilities in 2017 by 1.3% in this case. But the width of the 95% confidence interval for misestimation increases by 0.3. So there is increasing uncertainty because of the additional complexity. And we can use the misestimation to decide whether it makes sense to include this or the amounts of margins that we would need if we want to reflect this in our models.
Yeah. For example, if that cost, if the misestimation cost had been 2%, that would have told us that we don't really want to use the more complicated model because it would have eaten up any benefit that we would have had from getting that. So we mentioned basis risk earlier. So the classic definition of basis risk is that you're fitting a model based on one set of data, and then you're applying the model to a different set of data, and that'll generate basis risk. That'll generate uncertainty, and because those two sets might go apart. Classic example is you've got population data to fit your mortality improvements, and you've got a pension plan, and you want to know what the mortality evolution of that pension plan is. So that's a form of basis risk. But I invite you to think about basis risk also as having a simple model. Let's say a model for, you've got a model that describes the mortality behavior of your pension plan that you're interested in, but you decide only to use age and gender as the risk factors, despite the fact that you know that mortality is highly correlated with, say, the pension amount, or whether you're a surviving spouse or the original pensioner. So you've got a model that's too simple, and that'll cause you, in my view, what you should describe as basis risk. So you'll misestimate what the liabilities are because you've made too simple a model. So it's not just swapping in different data sets, it's also deciding to use a too simple model. So in that case, you can actually then use your estimation error to decide whether your model's good enough, whether the cost of including more risk factors is actually reasonable, or whether the additional risk factors introduce so much uncertainty that you pretty much can't use the model anymore. Okay? That's the trade-off. Yeah. But now let's talk about a real live mortality pool as a proper example.
So some of the examples above have already been referring to what we're calling the Mercer mortality model. And what it is just a pool of data that we've built at Mercer out of a number of large and medium-sized pension plans from across Canada. So there you see the map of Canada with the coverage, and it's so the data set we have data at the level of the individual, so we can use individual level survival models and include whatever risk factors that we have available, and the main ones we have are pension amount, color, and postal code information from which we can derive lifestyle information. So if we use that to the fullest, we end up being able to explain about 9 years of life expectancy differential at age 65, and we have over 100 unique curves. So this data set allows us to play around with adding various factors and looking at how it affects the model or subsets of the model. In this case, we'll look at a subset. So we'll look at, just to get a group that's reasonably well defined, but not too large, not too small, we'll look at males, white-collar pensioners, and who happen to be residing in Quebec. So that gives us 1650 deaths over a 10-year period. So, not that much experience, but enough that we can still build some models and get some idea about what the mortality should be. So if we do build a model just out of the experience for that subset, then we end up with a model that gives liabilities of about 4.77 billion, which would be equivalent to 92.5% of a particular table. And just providing that because in practice it's often necessary to express these results in terms of a standard table or some sort of internal basis. So everything's equivalent. Like if we get the liabilities, we can figure out what the equivalent loading is on the table. But because the group isn't all that big, the misestimation is still pretty substantial. In terms of liabilities, the 95% confidence interval would be about plus or minus 2.35%, while on the table it's about 7.5%. So this is still quite a large range. Now, depending on the purpose, that might be perfect. You might want to avoid basis risk altogether, use this result, and just have a large margin of some sort. But often, probably a little bit too much uncertainty. So one option would be to sort of borrow information from the Mercer mortality model from this larger data set and try to find a result that better balances the misestimation and the basis risk potential. So there's two options that we looked at here. One is just using pension as a risk factors, which would sort of be still is sort of the common way of handling such a problem. If that's the only, so this is using the whole data set, but just with this one risk factor, this one key risk factor. But in this case, we end up liabilities that are 4.2% lower than the group specific result. So it's I mean that might be the right answer, but it could be indicative that there's a basis problem here. But the misestimation confidence interval is much smaller at just plus or minus 0.75% of liabilities.
Sorry to interrupt, but just to drive the matter home, we're talking about $200 million that we theoretically could release from liabilities if we decided between those two models, like the portfolio-specific model or the pooled model, right? So that is an important question. And
so another sort of still dealing with pretty normal risk factors. Another option we could do is add color. So I mean, it's not surprising that this would make it closer since a subset is just white color. But what we get is a result it's still lower than the group specific model, but now it's just 0.8% lower. But because of the additional factor, the misestimation has grown from the plus or minus 0.75% confidence interval to the plus or minus 0.95. So here's the results in a sort of graphical way. So with the group specific on top, with the largest interval, then the simple model with just pension amount with the narrowest model, but way off from the group specific. In fact, the confidence intervals don't even overlap. And then the more complex pooled model with the color added, where the confidence interval is more reasonable, and the confidence interval is within the confidence interval for the group specific result.
Now this seems like a pretty natural spot to be in, but trust me, over the last 3 years that Stefan and I have been working together, we've spent many an hour on the phone debating which one it should be, and what the reasons are, and how to actually quantitatively figure out which of those mortality assumptions to choose. So do you use the equivalent of an industry table because you actually you believe those rates, you know that those are well-estimated rates, and it gives you the leftmost very tight confidence interval, and you can release that much of your liabilities? Or do you use the group-specific mortality, the red bar, where you know that there's a really wide range? Being able to quantitatively decide that is quite important, and being able to explain that or argue that is probably even more important. So, show of hands. Who'd go with the red estimate? Okay. It's my favorite too, but I'll leave it. Who would go with the green, dark green, the lowest one that's essentially based on a simple industry table, pretty much? Okay, and who'd go with the bottom one, the more complex pooled model? Okay, I think they're with you, Stefan. Okay.
And of course, we could also blend some of these results together. So one thing that we sometimes look at is blending, in this case, the red result, the top result, the group specific result, with the complex pooled model result. And misestimation confidence intervals allow us to know how much, basically, credibility to place on those two results, which can be quite powerful.
Okay, so that's not that argument that Stefan and I had isn't the only way you can apply once the input is detected. It's not the only way you can apply misestimation. And the next one is one that I'd like you to think about and maybe challenge me, because I'm still looking for someone who can really contradict this. So we've talked about model choice criteria, that's fine. But in my opinion, if you take the combination of process risk or stochastic risk and your estimation error or misestimation risk, if you combine those two, that actually describes the volatility of the actual portfolio. Right? That describes the volatility of financial outcomes for that particular portfolio of pensioners or portfolio of life insurance that you're reinsuring. You can use that to describe the volatility of the business, and then from that volatility of the business derive the margins that you have to hold for capital, the margins that you have to hold for prudential reserves. But that is a leap of faith that I'd like you to help me think about or challenge me, because where are we?
You want to be here still? Or?
Yeah. So because once we actually really know how volatile the business is, we can measure how volatile the business is, then we can explain exactly how much capital we have to hold, which risk we actually want. Even for risk selection, if you're an insurance company and you want to decide strategically which products to sell, if you can measure the volatility, then that'll be a very important decision-making criteria. Okay? Where are we? So one source of volatility is pretty much probably the biggest one, or the best understood, is that you have varying amounts. So if you've got life insurance and you've got a couple of lives that have literally hundreds of millions of life insurance coverage, and you have a large number of lives that have 100,000 or less of coverage, then obviously one or two of those big ticket risks causing a claim is going to be very expensive. Right? It's going to cause volatility. So it's the heterogeneity of your portfolio that's going to cause the volatility. And you can express that as that particular risk group having different mortality, if that is the case. And as we know, if we go to the next slide, this is a study that we did a couple of years ago, but that's been published in the European Actuarial Journal. We can actually show that for this particular group of German pensioners, the top 5% had on average 35% lower mortality. So these are essentially the managers in the pension plan, right? So a very large portion of the liabilities goes to cover that risk for that particular group. So if you can quantify what the mortality is, then you can actually measure the liabilities properly. And if you ignore it, you're going to misestimate those liabilities. So again, it's a question of basis risk or model risk. But it also means that I'm measuring the volatility of the entire block, because if I'm doing the runoff simulation, there is a small probability that one of these is going to actually cause, is going to die. It's a smaller probability. Okay, so the example that I had was setting the liabilities, the prudent liabilities for a pension plan, or setting the price for the reinsurance of a particular block of life insurance. But I mean, in pretty much every actuarial application, there is a need to know how certain or uncertain my assumptions are, and there's a value assigned to that. It's the prudential margins, if I have to hold statutory reserves, and with modern reserving methodologies essentially becoming pretty much prevalent across the globe, understanding the volatility of the business is going to be a core ingredient of setting reserves. Just like understanding the economic cost of taking on the risk is equivalent to setting the right level of capital. And if you want to optimize that, then of course you can use reinsurance to govern how much capital you need or what the reserve level is, simply because you can now explicitly model the uncertainty associated with that block. Okay. So we did that in a SOA-sponsored piece of research in 2016, where we essentially took the total cost of claims for a life insurance block. This was term life. We had a substantial amount of data, so it was a very rich data set. And the largest policy in that data set actually was $150 million. So if that person died, you would have immediately lost $150 million right there. So we modeled the volatility of this business, and we assumed different levels of reinsurance, so different reinsurance retention levels of a ceding company. We just arbitrarily posited that the ceding company without reinsurance would be making a 12% return on its economic capital that it would have to hold given the volatility of the business. And then we looked at how the distribution changed if you actually applied different retention levels. And what you can see is the distribution moves left because now the reinsurer is paying a larger and larger portion of the claims. That's the easy bit. But the distribution is also getting smaller or tighter. Right? You can see that as well. That essentially means that the risk is getting less, like the risk that the ceding company is retaining. And that if you've got those two offsetting elements of a cost to reinsurance, because the reinsurer isn't doing it out of the goodness of their heart, because they actually want money to cover the risk. So there's a cost associated with the reinsurance. Then you've got a trade-off between the cost and the benefit of the reinsurance in reducing risk. And that'll, like in this hypothetical example, if I've got a 12% return on capital for the gross position without any reinsurance, then increasing the level of reinsurance or decreasing the retention level will actually make your return on capital improve. So in this instance, we actually were able to lift it by 30%, right? Okay. So
we should point out that a lot of misestimations, the concept's been around for a very long time. I've seen papers from the 80s that are basically describing the general concept that what we talked about today. It's just back then computers just weren't powerful enough to make that practical. Not only because of the simulations, but also for the modeling in the first place. Like to build these models, it wasn't really practical. So the first paper there, the misestimation risk measurement and impact by Stephen Richards, is really the best modern summary of the underlying concepts. And in that, he's applying it to pensioner mortality. So that's a very important reference if you want more of the technical background.
Yeah, but if like some people don't like parametric models so much because they think that you're essentially smoothing effects in the data, you can apply misestimation to non-parametric models as well. But what you shouldn't do, you should never state a number without saying how good it is. Right? That's the one thing that I hope you'll walk away from this. So very happy to take questions. If you have any, if you want to grill us a little bit, there's a little bit of time for questions. Yep.
Tom Edwalds, DePaul University. Just a quick question. When we're estimating these liabilities, are you using a generational mortality table so that the trend is built into the table, or is that completely separate? You're using a static table for estimating liabilities and then adding the trend when you estimate the error?
So we're using static tables in this case, but to isolate the impact of the misestimation. But in theory, you can use any kind of projection scale on top. It makes the mechanics a little bit more complicated, a little longer to run, but perfectly possible. I mean, in an ideal world, you would do everything together. You would do the runoff, the misestimation, and some sort of trend risk analysis all in one place. But here we just, for simplicity, did it static.
Yeah, and specifically in the model that you showed early on, where there was this trend change, then the trend change already introduces additional misestimation, right? Okay.
Hi, Laurie Curtis, University of Waterloo in Canada. So I'm just wondering, I'm an economist, so we work more with survey data, and I know these are large administrative data, so the statistics are a bit different. But do you ever, to get more risk factors, look at using large administrative data sets? Survey data sets and looking at weights that apply?
Well, do you want to go first?
Well, I mean, for most of the analysis we're interested in, we need information on mortality by age at least, and ideally at individual level. So in general, we wouldn't think that would be available from survey data, but we certainly look at population data and other data to try to sort out what we expect the risk factors to look like at our portfolio level data.
Maybe if the next step between survey data where you're capturing socio-demographic features and the pure hardcore administrative data of a pension plan, a good step in between is using the residential postal codes that describe that have a very strong link to socioeconomics. There's a great story around that, especially when you look at the United Kingdom, where you have very deeply hierarchical postcodes that are very closely linked to the mortality experience. In Canada, there are a couple of challenges. We've essentially spent many an hour on the phone debating exactly where these challenges come from, but they're not quite as predictive as you would see in the UK.
And on the UK, they also have what they used to call the deprivation indices, which can be very powerful and helpful in terms of mortality, but we don't have that in Canada.
So if you don't ask any more questions, we'll run some models for you. That's a threat.
Now I get the chance to ask a question. Roland Rau from University of Rostock and the Max Planck Institute, also in Rostock, Germany. I would be interested, I think Solvency II tells you about what kind of confidence intervals you have to take, right? As someone also from another world, everyone's talking about their world where they come from. So I'm a demographer, I'm again a different world than most of the other people here. Who's taking the decision, what kind of risk do we take? Because, I mean, you estimate the distribution, include various risks. I think Solvency II tells you 99.5%, if I'm not mistaken. Is this a universal decision among insurance, reinsurance agencies or companies, or is this something someone has to take and say, we're happy with 80%, 90%, just out of curiosity?
May I?
Okay.
So the question is, it's twofold maybe. Who decides which confidence level or which value at risk level or conditional tail expectation to use for your capital assumptions? And then if you're talking about regulatory capital, it's a regulatory decision that gives you, that's prescribed by the regulator. There's an International Association of Insurance Supervisors that harmonizes the standards. But essentially, so it's not a subjective decision. However, deciding for whether it's a pension plan or whether it's an insurance company, the decision which level of risk that body is comfortable with, that is a management decision. That's an important strategic decision. And it may or may not depend on the regulatory definition of capital.
But it may affect your rating.
It may affect your rating, yes. So rating agencies, as Ronnie just mentioned, are very important as well.
I should mention with Solvency II, Solvency II is supposed to be over a 1 year horizon, so it's always unclear what that really means in terms of mortality. But there is a solid argument that should include the misestimation piece.
Hi guys, Tom Jones from Prudential. Great presentation, thank you. I have one question. There was a slide where you were sort of talking about the various, as you added parameters in or variables into your model, while you might improve your basis, your confidence interval is widening. So for example, if you included benefit tranching in your basis versus a simple model, the confidence intervals seem to be wider. And yet, you know, having done this for a while, I know that if you ignore those variables, you're really going to get a basis that puts you at risk for your liability. So when you're kind of looking at those confidence intervals versus the variables that you're including, how do you know where you were comfortable that you've optimized both so you can get to that valuation? Because it looked misleading to have a simple model have a tighter confidence interval. I think some might assume that would give you a better estimate or a better liability estimate. You could really be undervalued.
Yeah, so first thing, we sort of need to have always a minimally viable financial model. So so let's go all the way back up. So in this case, the model that doesn't even include gender wouldn't be necessarily a viable model for everyday use. We would need to be considered in a pension context to have a model that's minimally acceptable. We want to have at least gender, pension amount, banding of some sort, and also incorporate the mortality improvement. If we don't have that, then the model really isn't usable. And so to test that, so testing for the pension amount is easy. Just make sure that whatever tranches we use for the pension or salary, that it accounts for the amount effects or the salary effects. For other factors, though, to decide when we have enough factors, when the model is powerful enough, generally it's trying to look at the residuals. So looking at the model residuals and seeing if there's any patterns by age or by duration since commencement. And if there's patterns in those residuals, then we might have to add more factors. And at some point, we've either exhausted the factors or our model passes all the tests for statistical fit.
Yeah, I'd like to flip to the slide where we're essentially showing those confidence intervals for different essentially examples for model decisions. And the good thing about this somewhat more complex model, but that also relies on a larger data set, is that it fits within the confidence bands of the portfolio-specific assumption. So my inclination would always be to base it off the data and to make sure that I capture any signal that I can detect in the data of that particular group. As Stefan just said, looking at the residuals is a very important tool for understanding whether there are any effects that I've missed. But there are other statistical methods. For example, doing a bootstrapping experiment, you can just see whether your model actually predicts the actual deaths well enough. So using various different techniques, it's possible to tell whether the model is good enough. Then the other thing is how bad is the estimation error. So from my perspective, as a reinsurer, I'm used to not knowing things. I'm used to fairly large confidence intervals, at least conceptual, that I have incomplete information and my model is not going to be accurate. And I have to allow for that. But I have to allow for that in the correct range. And that's why my personal preference was the red model, because it tells me all I really need to know. The liabilities are somewhere between 0.65 and 4.65 and 4.9. And it's up to me to decide which level of certainty I need. Right? But it's, as the endless debates have shown, it's a very subjective decision. Yeah. Okay, so if there aren't any further questions, then I'll not make good on the threat to model, but I'll give you those additional couple of minutes extra break. But do feel free to come up to us and ask us any further questions.